Hello, my name is Eric Miller. I'm here with Dr. Raman Blanchard from Pendar Technologies. We're going to talk about an autonomous Raman system for analyzing trace residues on surfaces. This is one of a number of successful collaborations between academic partners at Alert and industry partners at Alert. So in particular, the Tufts Pendar collaboration has been active for 4 or 5 years now. It's basically the folks at Pendar have amazing expertise in the development and deployment of a variety of microscopy and optical systems. Tufts has been able to help a little bit on the algorithms and image analysis side. There have been 2 projects that we've sort of engaged in. The first was the standoff infrared system under the MODEX program run by the Homeland Security Department. But today we want to focus on the PCFIS system, which is an automated Raman microscope that Pendar has developed for to support the Army's mission.
Thank you, Eric, for the introduction. The system we're presenting today is indeed a Raman microscope, but it's maybe best understood as a surface analyzer in the sense that it's made to be used by non-expert user who would bring it to the field, place it on a surface, push a button, and let it run to try to identify automatically potential particles that would indicate trace contamination on the surface, potential explosives, explosive precursors, or narcotics. You can see a picture here of the system that we had to design to be compact and rugged. And at the core of the system is really that automation, the fact that the system does not require user input to scan a surface, find particles, and run Raman identification of those particles that were identified. The system was developed for the US Army for more of forensics type applications. But in general, the notion of having a non-expert user system that automatically find trace residues of threat material on surfaces is broadly applicable, including to DHS mission. Let me now describe what we did for this demonstration. So we placed some ammonium nitrate powder on a table, spilled some, and then took a napkin and wiped it a couple times completely off, so that from your naked eye, you couldn't tell that there was a powder left on the surface. Then we placed the instrument above that surface. What you see here is the interface for the instrument, and we're first manually adjusting the focus, and you see the live image going in and out of focus. And then what you see is that we take a survey, and we essentially start taking a stack of images that we're going to use to obtain an image that is sharp across the entire field.
Thank you, Raman, for showing us that demo. So I wanted to start now with discussing a little bit about this idea of an image stack, why we need it, and how we process it. So one of the complications associated with this Raman microscope is the need to image or to deal with surfaces that may not be flat, and which creates a number of complications in the analysis. So the reason we take an image stack is basically a collection of pictures taken at different focal lengths, so that different portions of the surface that we're looking at are in focus. By flattening the stack, we basically mean creating a single image that is, in some sense, all in focus. And this will allow us to basically provides what's necessary to localize all of the particles for later, or all of the particles for later processing. On the next slide, we sort of have a picture of what the stack looks like. Essentially, what we do is we chop the images up into little squares. We compute a focus metric, that is a metric that says how well or how sharp the image is in each of those little regions. And the higher the metric, the more in focus. And then by basically taking the maximum focal value along Z, we figure out which of the many image planes are the most in focus for that particular area of the image. and the results are shown on the next page. So this is essentially a full image. We chopped it up into blocks that are about 30 by 30. For each block, we computed for every image in the stack along those blocks, we computed a focal metric. The maximum value of the focal metric then gives us the layer of that block that's most in focus. And on the right is the flattened image. So this is a picture where we basically pull from each of the planes, the most in focus planes, the information, and put it into one picture. And you can kind of see here that everything is sharp.
Once we have a flat image that is sharp across the field, we can locate particles. You see here, bottom left corner, the list of located particles. And if we click on any of them, we will get a zoom in picture on the corresponding particles. Now, Eric is going to tell us a bit more how we obtained that list in the first place.
Particle localization is really done in a couple of steps. The first gets rid of all of the things that aren't particles in the image. So this is called image normalization. Essentially, what's left are structures that we're pretty confident are only or at least mostly particles. Once we've normalized the illumination, it's pretty easy to develop to turn that image into a mask. So basically, a binary image, where everything is either a particle or background. And once we have a binary image, it's standard image processing, morphological image processing to associate labels with all of the connected components. So each of the little clusters of connected pixels then would count as a single particle. So really the only reasonably complicated step here is illumination normalization. It's relatively simple. Basically, we take a logarithm. So taking the log of an image is sort of increases the contrast. Stuff that we're trying to get rid of are mostly those large horizontal bands, which are in some sense low frequency. So the second step is to take a DCT, a discrete cosine transform, remove all of the low frequency component, take an inverse discrete cosine transform, gives you the object of the image on the center of the bottom row. We exponentiate and we get the image on the right side, in which basically all of the low frequency structure, the horizontal bands as well as the vertical stripe on the right, have been eliminated. And the only stuff that's left, although it's a little difficult to see, are our pixels associated, or the only non-zero pixels are associated with particles. And as I said before, simple thresholding and morphological operations kind of get those, bring those out and let us identify individual particles by connected component analysis.
Going back to the particle that we had singled out earlier, we can now ask the system to bring the Raman laser focused onto that one particle and run the chemical identification routine. The system integrates the signal for a few seconds and then return the identification, here ammonium nitrate. Eric will now describe what it takes to do that aiming and focusing of the Raman laser accurately to ensure good results.
So the last step in the processing is basically refinement for particle by particle analysis. And this has to be done in both the Z dimension as well as X and Y. So the first thing that we do in this step is to refine the Z position. So essentially, this amounts to repeating the flattening process, but this time using all of the data, so all of the information in all of the very finely obtained slices, but only in the vicinity of the particle that we're looking at. The second issue is localizing the particle basically in the crosshairs of the microscope in XY space. And for various reasons, we may not know exactly, the system doesn't know exactly where the particle is, at least based on the initial set of processing that's done. So what we do is we move the system over to roughly where the particle is, where we think it's centered. We take a new picture, identify the particles in that picture, and then from that picture and the reference picture that we had, the reference flattened image that we had from the previous step, we use the technique called template matching, which basically can identify vertical and horizontal offsets of the image to let us know how many pixels, or perhaps even pixels and fractions of pixels, we need to slew the camera so that it's precisely positioned exactly over the particle, and we can do the chemometric analysis.
So that's basically how this instrument works. And by repeating the same process, the instrument is able to go from particles to particle and keep identifying them, slowly populating this list with the names of the chemicals that have been identified. Now here we use the instrument manually, but there is also a more automated mode where the user would press a single button and the whole process that we described today would run automatically through all the steps, from the image analysis, particle location, and then driving the system for the chemical analysis of the various particles, slowly populating the list with the names of the chemicals identified. We hope you enjoyed this presentation. We're now available if you have any questions. Thank you.